All right, so I recall some very basic facts in 2 dimensions. So in 2D, I consider a surface sigma with some metric G. And it's very classical that if you deform conformally the metric in this way, so I write G tilde e to the 2W times G. Then we have this nice transformation law for the Laplace operator. So delta G tilde is e to the 2 minus W times delta G. And we also have a nice transformation law for the Gauss curvature. So if Kg is the Gauss curvature of sigma G, then we have this equation, so minus delta G W plus Kg equal to Kg tilde times e to the 2W. So very simple formula. In particular, if you integrate the Gauss curvature, so also recall that dVg tilde is e to the 2W times G, then the integral of Kg dVg over sigma, if sigma is compact, is a conformal invariant, and in fact by the Gauss-Bonnet theorem, this is nothing but 2 pi times the Euler characteristic of sigma. So this is the situation in 2D. Let's look in 4 dimensions. So there are some kind of partial analogs. Okay, in 4D, there is a scalar quantity which is called Q-curvature. And it's defined in this way. So Qg, so I consider now a 4-dimensional manifold, M4, still with metric G. And the Q-curvature is defined as 1 over 12 times R squared minus 3 Ricci squared minus delta R. And this was defined by Branson in 1985. Okay, so let's look at the transformation law for the Q-curvature when we perform a conformal change of metric. Okay, so we set again G tilde e to the 2W times G. Okay, and then the transformation law is the following. So I have to substitute minus Laplacian with this operator, Pg. I will tell you what it is. So the transformation law for the Q-curvature is the following. Pg of W plus 2Qg is equal to 2Qg tilde times e to the 4W. Okay, what is Pg? Pg is the following operator. So the principal part is the Laplacian squared of phi. And then you have to add some curvature terms, minus divergence of 2/3 Rg d phi minus 2 Ricci d phi. Okay, and this operator is called the Penny's operator. So it was defined by Penitz in 1983. And there is an analogous transformation law under conformal change of metric. In fact, Pg tilde is e to the minus 4W times Pg. Okay, so not only this, but there is also a kind of similar Gauss-Bonnet formula. So in 4D, if you integrate the Q-curvature, and if you add 1/8 times the Weil tensor squared, then you get 4 pi squared times the Euler characteristic of the manifold. So maybe many of you know that the Weil tensor squared is a pointwise conformal invariant. So Wg tilde squared is e to the minus 4W times Wg squared. And this implies that the Q-curvature integrated, so if I denote Qp, the integral of Qg over m in dVg, this is a conformal invariant. Okay, so this is very important. In fact, let me recall that from the last lectures by Bent Gursky, the Q-curvature is 1/2 times sigma 2 of AG, the Schouten tensor, minus 1/12 times the Laplacian of R. Okay, so if you integrate it over the manifold, then you get 1/2 times the integral of sigma 2. Okay, and we saw from the last lectures that there are indeed the geometric applications to the study of 4 manifolds. So let me mention some. So I will go very quickly because the applications are many and there will be maybe more focused talks. There have been and there will be. So let me not go into them, but let me just mention some. So as I said, so there are applications to geometry or topology of 4 manifolds. Especially the Q-curvature was used as the first tool to study the sigma 2 equation. So Chang, Gursky, and Yang somehow deformed this term into the equation. So they started with a solution for the constant Q-curvature equation. So I will discuss that in particular. And then they deformed this quantity to get metric with positive sigma 2. So if you have a positive scalar curvature, or say positive Yamaha invariant, and positive sigma 2, then you get pinching information on the Ricci tensor, and you have nice geometric consequences. Okay, so here I mention results by Gursky, and then Chang, Gursky, Yang. So this is one application. Another one is the study of the so-called functional determinant. So in 2D, there are the so-called Polyakov or Raysinger formulas. And there are some analogous formulas in 4D by works by Branson and Ørsted. Okay, another application is the construction of ambient and Poincaré matrix. By the works of Pfefferman-Graham, Graham and Irachi, and Graham and Zworsky. So also in the lecture of Ching, you know also the applications to scattering theory, volume renormalization, and so on. So the Q-curvature also enters in these questions. Other things are the construction of global conformal invariants. So one of the, in fact, goals of the construction of the ambient metric was finding new conformal invariants, and also some conformal Hodge theory. And for this I can mention works by Branson and Gover. Applications to quasi-conformal mappings. So there is very recent work in 4D by Bonk, Heinonen, and Saxman. Compactifications of locally conformally flat for manifolds there are works by Cheng, Qing, and Yang. And finally, I also want to mention some questions in mathematical physics. So study of problems in statistical mechanics. And to the Dirac equation. And about this, there are works by Kissling, who generalized the previous works by Cianillo and Kissling about the Gauss curvature equation, and Hijazi for the Dirac equation, in particular the spectrum of the Dirac operator. So lower bounds on first eigenvalue and such things. Okay, so somehow in the spirit of classical results like the uniformization problem, the Amabi problem, finding metrics with a constant sigma 2 or so. Here you have a similar question. So can you find somehow standard metric on a four manifold which enjoys particular properties? So in particular, the question I will address. So question, so can one find on a given four manifold M with metric G a conformal metric G tilde for which Q G tilde is a constant. Okay, so I will discuss first the situation in 4D. Next week, if there will be time, I will also mention the problem in higher dimension. So what is known about this problem? Well, there was a first result. So a theorem which I call theorem 1 by Cheng and Yang. Back to 1995. So the answer is yes, provided the following condition holds. So suppose that the Penning operator is positive definite. So, and I mean strictly positive except for constants. So notice that the constants always belong to the kernel of the Penning operator, okay? Because the Penning operator acts on the differential of a given function. Okay, and also assume that QP is less than 8 pi squared. Okay, then MG has such a conformal metric. So then there exists, say, G tilde in the conformal class of G such that QG tilde is equal to a constant. Okay, so what does this problem boil down to? So let's look at the transformation law for the Q-curvature. Okay, so the new Q-curvature is given by this equation. Okay, so I want to find a conformal factor for which QG tilde is a constant. Okay, so this means that the problem is equivalent to solving this PDE, so which I call PG of U plus 2 Qg equal to 2 Q bar e to the 4u, okay, with Q bar real constant. Okay, a very useful comment is that, in fact, the problem P is variational. So, and in fact, it's equivalent to finding critical points of some functional, which I denote by 2 of u. I will also say a few words about the notation. So this is defined as the integral over m of u pgu dvg plus 4 times the integral of qg times u over m in dvg minus qp, so the total Q-curvature, times the log of the integral of e to the 4u dvg over m. So just a couple of comments about this functional. First of all, why calling it 2? Well, in fact, the notation is related to the functional determinant. So there is a theorem that tells you that if you compute the variation of the logarithmic determinant and if you take the ratio under a conformal change of metric, there is a global decomposition into 3 terms, which are denoted by 1, 2, and 3. There are different coefficients, and 2 is just a second of these 3 functionals. So it's a universal decomposition. And second, this is somehow consistent with the fact that the constants are in the kernel of PG. The functional 2 is invariant if you add a constant to u. Okay, so 2 of u plus c is equal to 2 of u for any c in R. Okay, and this is in fact useful because you can somehow normalize the domain as you want. So useful normalizations are either u bar, which is defined as the average integral of u in dvg equal to 0, or the integral of e to the 4u over m dvg equal to 1. So this will be the total conformal volume of the new metric. Okay. So the natural space in which defining this functional is h to 2 of m. Okay, so we require that u, gradient u, and gradient squared of u belong to L2 of m. So why? Because here you can integrate by parts, and the main term in the quadratic part of the functional will be the Laplacian of u squared. Okay, so you required the second derivatives to be in L2. So that's the natural functional space. Okay, so some remarks. So remarks. So this is remark 1, say. So A, if QP is negative, then the solution is unique. And this follows from the fact that the functional 2 is indeed convex under this assumption. And the second is that Brendel in 2003 proved a higher dimensional extension of theorem 1. Okay, so I will prove, in fact, this theorem. So the fundamental tool to prove such a result is the so-called Adams inequality. Which is a four-dimensional extension of a classical Moser-Trödinger inequality. So this has been proved by Adams in the case of flat domains. And by Chang and Yang on four manifolds. So the Adams inequality, in fact, allows you to control the last integral term in the space H22 of M. Okay, so the assumption is that the dependence operator is positive definite. Okay, so then there exists some constant which depends on M and G, such that the integral of e to the 32 pi squared u minus u bar, the average squared, so the exponent is divided by the integral of u pgu, okay, over m. You integrate this quantity in the Vg, okay, and this quantity is bounded by that constant c for any u in H22 of M. Okay, so the quantity at the numerator of this exponent is a function. Okay, the denominator is a number which depends on u. Okay, I will just say a few words about the proof. So maybe I want to keep this. Well, the idea of the proof so is to use the Green's representation formula for PG. Okay, this is an elliptic self-adjoint operator, so there is a Green's kernel. And actually, the Green's function was started by Fontana and Branson, Chang and Yang. Okay, and the asymptotics of the Green's function for the dependence operator is the following. So it's the same as the asymptotics of the bilaplacian. So the main term is the logarithm of 1 over x minus y. So you have a logarithmic singularity with that coefficient. And then you pick up lower order terms. Okay, that's all I want to say about the proof. Okay, and as corollary, which I will call the weak Adams inequality, is the following. So there exists another constant c prime equal to c prime of m and g, such that the log of the integral of e to the 4 u minus u bar is bounded by 1 over 8 pi squared times the integral of u pgu m dvg plus c prime for any u in h22 of m. So the proof is one line. So proof of corollary. Okay, just use the Schwarz inequality in this form. So for u minus u bar is bounded, I hope I got the coefficients right, by 32 pi squared u minus u bar squared divided by the integral of u pgu over m. So this is a constant, okay, plus 1 over 8 pi squared integral of u pgu m, okay. So you integrate, sorry, take the exponential, integrate, and take log. Okay, so that's it. Of course, you have to use the stronger form of the Adams inequality. So now comes the proof of theorem 1. So that theorem. Okay, so first of all, I use the invariance of the functional by adding constants, okay, and I can subtract the average of u. So 2 of u by that invariance is equal to the integral over m of u times pg of u. So here the average of u cancels if you subtract it, dvg, plus 4 integral of qg u minus u bar minus qp log of e to the 4 u minus u bar. Okay, so now we just use the weak Adams inequality. So this is greater or equal than minus qp log of, I'm sorry, then 1 minus qp divided by 8 pi squared times the integral of u pgu m dvg, okay, plus 4 times the integral of qg u minus u bar. Oh, by the way, here I'm assuming that qp is non-negative. It will be even easier for qp negative, okay. Now I can control this term using the Poincaré inequality. Okay, as I said, the main term here is the Laplacian of u squared. Okay, so this is bounded by Poincaré by 1 minus qp divided by 8 pi squared minus epsilon integral of u pgu over m dvg minus c epsilon. Okay. So, but now the Penit's operator is positive definite. Okay. So this means that the value of this quantity is going to infinity when the norm of u tends to infinity. Okay. So this means that the functional is coercive. Coercive. So tends to infinity at infinity. Okay. And this means that you can just find a critical point by minimization. Okay? So this implies that there exists a global minimizer. So this means tends to infinity as normal view tends to infinity. Of course, I'm modding out the constants, okay, because the function is invariant, adding constants. Okay, when QP is negative, it's even easier. So you don't even need to use the Adams inequality. For QP negative, you can use the Jensen inequality. Okay, so you know that if you have a measure space X with measure mu, and some function phi which is convex, then phi of the integral of f in the mu is less or equal than the integral over x of phi of f in the mu. Okay, so we use it for d mu equal to dvg over the total volume of M. Okay, and phi equal to exp phi of s equal to exp for s. Okay, so in this way you find that e to the 4 times the integral of u in dv over v of m is bounded by the integral over m of e to the 4u dv over v of m. So if you take the log, okay, and use the fact that minus qp now is positive because qp is negative, then you can just bound minus qp times the logarithm by the integral of u. And then you can just repeat the same proof. It's even easier. Okay. Any questions so far? Yes?
What is the Poincare inequality that you're using there?
Oh, you can bound the L2 norm of a function with zero average by the integral by the L2 norm of the Laplacian.
But you are doing the Chinese operator over there, right?
Yeah, that's okay. I mean, it works for because the principal part of the dependence operator is the Laplacian squared, and then there are gradient squared terms, but still you have a Poincare inequality for such operators. Yeah, so I'm using the Adams inequality here, the Poincare inequality, and well, yeah, yes. In fact, today, in the second hour, I won't discuss the case in which the dependence operator is not positive definite. Okay, so this concludes the proof of existence. So what should I erase? Maybe I continue here. Okay, on the other hand, there are many examples of manifolds for which QP is larger than 8 pi squared, and in fact QP can be arbitrarily large. So if you know about the Yamabe problem, there is this conformal invariant which is called the Yamabe constant, okay? That is always bounded above by the Yamabe constant of the sphere, of the standard sphere, okay? It is not the case for QP. So QP is a conformal invariant, but there are no upper or lower bounds on four manifolds. So one example is if you take M to be the product of two manifolds, sigma 1, sigma 2. so with a constant Gauss curvature matrix, okay? So in this case, the total Q-curvature, so QP is 2/3 pi squared times the Euler characteristic of Q1, I'm using the Gauss-Bonnet formula here, times the Euler characteristic of Q2 minus 1/6 pi squared times Euler characteristic of sigma 1 squared plus the Euler characteristic of sigma 2 squared. I'm not sure you see here, maybe not. So minus 1/6 pi squared chi of sigma 1 squared plus chi of sigma 2 squared. Okay? So the characteristic, Euler characteristic of surfaces is quantized. Okay, so it can be positive for the sphere, 0 for the torus, and then arbitrarily negative if you take a torus with a large number of handles. Okay, so if sigma 2 and sigma 1 are such tori, okay, and if you take, for example, the Euler characteristics to be the same, then you see that the QP can become arbitrarily large. Okay, so this is one example. And so the theorem which I would like to discuss in these lectures is a result by Jadley and myself, so a theorem from 2005, in which we extend the result of Cheng and Yang. Okay, this is our result. So suppose that PG has a trivial kernel. So the constants are always in the kernel, but we assume this non-degeneracy condition. And also that QP, so the total Q-curvature, is not a positive integer multiple of 8 pi squared. So QP is different from 8 pi squared, 16 pi squared, 24 pi squared, and so on. Okay, then P is solvable. So we can find indeed a conformal matrix with the constant Q-curvature. Okay, some remarks. So remark 2. So the assumptions as for also theorem 1 are conformal invariant and also generic in this case. So conformal invariance follows from the conformal invariance of QP, okay, and also from the invariance of dependence operator. So I recall that PG tilde is e to the 4w times PG, okay. So PG tilde has trivial kernel if and only if PG has a trivial kernel. But there are cases which are not covered, do not cover. So despite they are generic, do not cover interesting cases. For example, locally conformally flat manifolds with even Euler characteristic. So recall that if you integrate the Q-curvature, and if you add 1 over 8 times the Weil tensor squared, you get 4 pi squared times the Euler characteristic of the manifold. Okay, so locally conformally flat means vanishing of the Weil tensor. Okay, so in the locally conformally flat case, QP can be multiple of 8 pi squared if the Euler characteristic is even and positive. Okay, and notice also that if you plug in the sphere into this formula, okay, so Weil will be 0, the Euler characteristic is 2, so QP for the sphere is precisely equal to 8 pi squared. Okay, so that's why this number 8 pi squared appears in this theorem and also in theorem 1. That's a kind of delicate case, which I will discuss probably in the next lecture next week.
Also, not assuming anything of the scale calculation.
Nothing. That's it. In fact, we saw by the lectures of Gursky that if the scalar curvature is positive, then automatically the total Q-curvature, QP, is less or equal than 8 pi squared. So in particular, we can cover cases when the curvature is negative here, as for products of negatively curved surfaces. Okay, so this would be remark A. Just some comment about the difficulty of this extension. So the new cases are when lambda 1 of PG is negative. Okay, so we allow negative eigenvalues. Or when the total Q-curvature is greater than 8 pi squared. Or when you have both these conditions. So just to be heuristic, say if I would evaluate the scale of difficulty, I would say 1 here, maybe 10 here, and 11 here. Okay, so today I want to cover this case. Okay, but I will describe, say, the general strategy for solving the problem. All right. So we saw that when QP is less than 8 pi squared, then the functional is bounded from below. Okay. So I want to show you that if either these conditions hold, then this is not anymore the case. This is not the case anymore. Okay. So I want to describe the loss of coercivity. And then we can take a break. Oh. Lost my notes. Okay. There's a lot more down there. Okay, so loss of coercivity. So I recall coercivity means the functional goes to plus infinity when the normal view goes to plus infinity. Okay, so let's examine the case in which lambda 1 of PG is negative. So this is very easy to see. So this means that there exists some V1 different from 0 in H22 of M, such that PG of V is equal to lambda 1 times V1. Okay. So just some comments. The integral of V1 will be equal to 0 just by integrating this equation. So PG has a divergent structure. Okay. And also v1 belongs to L infinity of m. Because this is an elliptic equation, okay, linear elliptic equation, so you have all kinds of regularity. In particular, eigenfunctions are bounded. It is not true for functions in H22, but this solves some nice PDE. So it is. Okay, let's take t positive number, and let's evaluate the functional 2 on tv1. So this is t squared integral of v1 pgv1 plus 4t integral qg times v1, and then minus qp log of the integral of e to the 4t v1. So lambda 1 is a negative eigenvalue. Okay, so this integral is the integral of lambda 1. So v1 pg v1 is lambda 1 integral of v1 squared, which is negative. Okay, this is easy. Okay, so some linear function of t. And about the last term, e to the 4t v1 belongs to e to the 4t inf of v1 over m, e to the 4t sup of v1 over m. Okay, so this means that when you take the log of e to the 4t v1, this is a big O of absolute value of t times the norm of v1 in L infinity. Okay, so what's the conclusion? Okay, 2 of tv1 is equal to lambda 1 integral of v1 squared times t squared, okay, negative coefficient of t squared, plus big O of t. Okay, so this goes to minus infinity when t tends to plus infinity. Okay, so the norm of the argument is going to plus infinity, the functional is going to minus infinity. Okay, this is not coercivity. Yeah, the functional is here. Okay, so maybe I erase nothing. I just use this blackboard. Okay, so let's look at the case qp greater than 8 pi squared. Okay, so if lambda 1 is negative, we don't have coercivity. It's also the case when qp is greater than 8 pi squared. And this is due to bubbling. Okay, so a word you like a lot if you sit if you sit here. Okay, and the test function will be actually a standard bubble. Okay, so you fix a point x in the manifold. Okay, and you choose this test function. So this is the conformal factor of the stereographic projection. So all of you should know. So the log of lambda over 1 plus lambda squared. So this is a function of y. Okay, x is a fixed parameter. X minus y squared. Okay, so you use some say local coordinates and glue this bubble to the manifold. So what's the picture of this function? So the maximal value is log lambda. Okay, if you say isolate some ball b delta, so this will be b delta of x, the peak, this function is closer to minus log lambda. Okay, so this will be the picture. Okay, and then you can somehow so when you want to compute the different terms in the functional, you can regard phi lambda x to behave in this way. Say to log lambda being close to log lambda for, say, x, y minus x bounded by 1 over lambda, minus 2 log of mod x minus log lambda for 1 over lambda bounded by x minus y bounded by delta. So delta is a fixed constant. And minus log lambda for x minus y greater or equal than delta. Okay, so this implies that when you compute the integral of qg times phi lambda x, this is somehow close to the average of phi lambda x times the integral of qg. And this is minus log lambda times qp. Okay, because you can regard this function phi to be the constant minus log lambda away from this ball b delta. Okay, the integral inside b delta is somehow negligible. But when you compute the Laplacian of phi lambda x, this is of order 1 over lambda squared for x minus y bounded by 1 over lambda, minus 4 x minus y squared for x minus y between 1 over lambda and delta, and say big O of 1 for x minus y. Can you see here? Greater or equal than delta. So this implies that the Laplacian of phi lambda x squared is of order 2 pi squared. So this is the surface of the unit sphere in R4 times 16 plus little o of 1 times log lambda. And finally, if you look at e to the 4 phi lambda x, this converges weakly in the sense of measures to some c naught times the Dirac delta at the point x when lambda goes to infinity. So this implies that the integral of e to the 4 phi is uniformly bounded above and below by constants. So when you take the log, that's bounded. Okay, so in conclusion, you find that 2 of phi lambda x is equal to 32 pi squared minus 4 qp, because there was a 4 here, log lambda plus lower order terms. Okay.
The quadratic gradient terms and the dependence operator, those are much lower order.
Yeah, that will be lower order. Yes. So the main term is the Laplacian squared. Still, this is a loss of coercivity. Okay, the norm of this function is going to plus infinity. Okay, if qp is greater than 8 pi squared, this tends to minus infinity when lambda goes to infinity. Okay. So we saw that either when lambda 1 is negative or when qp is positive, the functional is not coercive, so it's unbounded below, and this means that we have to find saddle points if we want to find critical points. So in the next hour, I will discuss the general strategy to find critical points and apply it to this case.
So we have a 10 minutes break.
Okay. So, yeah, I would like to prove part of this second theorem. So, finding solution of this equation when the Euler function is unbounded from below. Okay, so when you have no chance of minimizing, and so we want to find critical points which are in general saddle points. Okay, and I would like to start with some abstract nonsense, which is a min-max theory. Okay, so very abstract construction. So the idea is to study some variational problem, so some functional, and you use gradient flow to the form sublevels of a functional. Okay, so you let these sublevels evolve, and you have two possibilities in general. So either along some line flow you encounter a critical point, which would be nice, or you don't find any critical point, which means that in general you can deform one sublevel into another. Okay, and this will lead you to some homeomorphism between different levels, different sublevels. Okay, so the idea is to try to understand the topology of different sublevels of the functional, so that if you detect a difference in topology, you cannot have a homeomorphism, so there should be critical points. That's the idea. Okay, so how to do that? So this will be the setting. So H, a Hilbert space, and f from H into R as a two functional. Okay, so it's very important to have some kind of compactness condition, which is called the Pallet-Smale condition. So what does it mean? So definition. So f satisfies the PS condition if for any sequence un contained in the Hilbert space H, so satisfying these two properties, so with f of un converging to some real number, okay, and such that the gradient of f at un tends to 0, if for any un, then for any un satisfying these conditions, un has a convergent subsequence. I mean strong convergence. Okay. So examples. So take f, so h to be r, okay, and f of x just to be the function x squared. Okay, very stupid examples. So this will be the function, okay. So take a sequence of points for which the gradient is going to 0, then this converges to 0. Okay, so this is an example of stupidity squared. One example which is a little less stupid, so this actually satisfies the Pallet-Smale condition. Take this example, h equal to r, f of x equal to 1 over 1 plus x squared, this does not satisfy the Paley-Smale condition. Okay, so this will be x, f of x. Okay, and this does not satisfy the Paley-Smale condition because you can take a sequence xn equal to n. Okay, so the function is converging, the gradient is converging to 0, but the function xn equal to n does not have any convergent subsequence. Okay, this is in fact the tricky part here. If you follow a gradient flow for this functional, this will bring you to infinity. Okay, that's the point. So flow lines do not stay compact. Okay, Paley-Smale condition is used to prove compactness of flow lines along the gradient. So we will see how it is used, but this is to give you the idea. Okay, so an important business here is the so-called deformation lemma. So what does it tell you? Exactly one of the two alternatives above. Okay, so suppose that f from h into r is C2, satisfies the Paley-Smale condition, and that a, b are two numbers a less than b. Okay, then either f has a critical point in the strip as f between a and b, okay, or exactly the deformation lemma, the sublevel f less or equal than a is homeomorphic to f less or equal than b. Okay, so the idea is that Paley-Smale implies compactness of flow lines, so either you are stuck at a critical point or you can keep going. So the proof, okay, so let's construct some gradient flow or something similar. So I define this vector field v to be minus the gradient of f divided by 1 plus the norm squared of gradient of f to the 1/2. So I just define it because the gradient of f can be unbounded, okay, but this vector field v will actually be bounded. Okay, and now I consider this Cauchy problem. So x dot of t in h equal to v of x of t, with x of 0 equal to some x naught in h, which is in the sublevel f less or equal than b. So f of x naught less or equal than b. So the idea is that the vector field decreases the value of f. In fact, so let's take f of x of t, and let's take the derivative with respect to time. Okay, so this is equal to gradient f scalar product with v in h, and this is minus the gradient of f squared divided by 1 plus gradient of f squared to the 1/2, which in particular is always negative if f is non-zero. Okay, so suppose that the first alternative is false. Okay, let's argue by contradiction. Suppose there is no critical point in that strip. Okay, so either 1, sorry. Okay, so I make a claim that there exists delta positive such that, in fact, not only this derivative is negative, but it's bounded from above my minus delta. Okay, so there exists a delta such that d dt of f x of t is less or equal than minus delta as long as f of x of t is greater or equal than a. So as long as we are in the strip, v really decreases the value of f. Okay, so I want to avoid situations of this kind. That's the point of having the Pallas-Mail condition. Okay, so otherwise there exists some sequence Tn such that f of x of Tn is decreasing, but always staying greater or equal than a. Okay, with the gradient of f of x at Tn tending to 0. So if this quantity tends to 0, okay, then also d dt of, if this tends to 0, then also the gradient of f has to tend to 0. Okay? But this is telling us that x of Tn is a Pallas-Mail sequence. Okay, so this is converging. Okay, so must converge up to a subsequence to some x bar, and x bar will be a critical point of f. With f of x bar between a and b. End of the proof. Okay, oh, by the way, about the homeomorphism, okay, so if there is no critical point, I'm sorry, I'm not quite finished. So the gradient flow would strictly decrease the functional, okay, and then to find the homeomorphism is, so this means that, sorry, let's erase the square. So if 1 is false, okay, then we have this condition. So this means that every x naught in the sublevel f less or equal than b reaches the sublevel f less or equal than a in finite time. Okay, so this allows actually to construct, because f is decreasing with negative speed, okay, it's strictly decreasing. So if I just apply some rescaling in time, then I find the homeomorphism. Yeah, but it's no, even homomorphic is okay. You just rescale in time.
So like the point is there's a fixed delta which works for all t in this range.
That's a point, yes. And for all initial data, yes. So you're really avoiding these kind of situations. Oh, the homeomorphism follows from the well-posedness of the Cauchy problem. So because you have somehow local uniqueness, and then you get the homeomorphism, not only homotopy. Okay, so questions so far? All right, so some applications. Okay, so suppose we are in the same situation as before. So I want to state this proposition. So how do you apply the deformation lemma to find the critical points? So proposition 1, so let A be a compact topological space. I'm thinking of something, say, standard, okay? Balls, intervals, things of this kind. And some set B, which is contained in A, closed. Okay, nothing fancy for the moment. So an example would be the ball in n dimension and the boundary Sn minus 1. So this would be a typical example. I mean, this is actually the one I will use today. Okay, so now I consider this, so a map, say HB, from B into H, which is continuous. Okay, and I define a class of maps, okay, which I call GAB. So these are the maps H from A into H, which extend HB. So such that H restricted to B is equal to HB. Okay. So now let F in C2 of H satisfy the palette-Smale condition. And suppose that this condition holds. So this looks very abstract, but I will try to explain. Okay. So this condition star holds. So what does it mean? There exists a positive delta such that the sup for y in A of f of h of y is greater or equal than the sup for x in B of f of hb of x plus delta. So I require this to be true for any h in G AB. Okay, so first of all, I take B, smaller subset of A. Okay, I consider this map HB, which is continuous, and then I look at the extensions in A of this map. And then I look at the suprema. Okay, so the supremum over this larger set will be, of course, greater or equal. I'm requiring that there is some gap here. Okay, so the difference between the sup is bounded by some delta positive. Okay, so now I define this number. I know that everything looks okay, nonsense. Okay, but I will apply to concrete cases. So CAB to be the infimum for all the maps H in GAB of the sup of f of h of y, y in A. Okay, so this is what you call min-max. Okay, first of all, take some fixed h in this admissible class of maps and look at the sup. Okay, and then I take the inf over all the admissible maps. This is min-max. Okay, so then CAB is a critical level for f. So f has a critical point at this level. Any question about the statement? I know you are all lost, but yeah. I will apply to, say easy cases, okay? So far, everything looks very abstract, okay, and it is. So let me give you the proof, okay, and then the examples. So proof, okay. So I call C naught this number. So the supremum of the image of B. Okay. So what's the situation? Okay. Here is C naught. Okay. Here is C naught plus delta. Okay. And somewhere here I have CAB, which is greater or equal than C naught plus delta. Okay. First of all, I define, so this is, say, S. I define some cutoff function chi of S, which has this form. So is 1 for S greater or equal than C naught. And then, I'm sorry,
C naught depends on H.
I want to put it here. C naught, of course, yeah, it depends on H, right? HB. Okay. So I define a cutoff function in this way. So 0 for S less than C naught, and 1 for S greater or equal than C naught plus delta. Okay. So if CAB, this is, I told you, this is abstract nonsense. Okay. So if CAB is not critical, you can find some epsilon, okay, say less than delta over 4, such that f has no critical points in this range CAB minus epsilon, CAB plus epsilon. Because otherwise, you would get, this follows from the Paley-Smale condition. So you would get a sequence of critical points with energies tending to CAB, okay? Look at the Paley-Smale condition. So the gradient of f at these critical points will be exactly 0. So that would be a Paley-Smale sequence which has to converge to a critical point of f exactly at level CAB. But there is no such critical point, okay? So there are no critical points in this strip. And now I define, so I go back to the definition of CAB. This is the infimum of those suprema. Okay, I know you are all lost, but if you look at the blackboard, every step is correct. Okay, so let H epsilon in GAB such that, so the sup for y in A of f of h of y is less than CAB plus epsilon. Okay? All right. So now I want to use the deformation lemma. Okay, deformation lemma tells me that if there is no critical point in this range, then I can deform this sublevel into this one. Okay, but there is a trick here. So I want to start with this map H epsilon, okay, which lies in this class, and I want this to be preserved under the flow. Okay, so I want to consider a one-parameter family of maps in GAB. Okay, so what does it mean? That the value on B has to be fixed. So I add a cutoff function which preserves the set B, so the image of B. So apply this the flow of chi of f of u times v of u. So v is the same vector field as before. Okay, so this generates some one parameter family of maps T, which I call chi v h epsilon. Okay, so look at chi. So if I'm at a point where the value of f is less than c naught, so in particular all the images of HB are in this set, then the flow doesn't move this point because chi is 0. Okay, but it will move the points above c naught plus delta. Okay, so this is somehow the situation. So you can take B to be as 0 and A to be as 1. Okay, so this will be just an image of an interval into the Hilbert space, and this will be the value of f. Okay, so this will be A and this will be B. So what's the point? That so C naught is here, okay, and CAB is strictly above C naught plus delta. Okay, so when I use this flow, okay, I'm somehow fixing this part, okay, below C naught, and I'm just deforming the top. Okay, so this is still an admissible map if I flow it. Okay, so what would be the contradiction? The contradiction is that the deformation lemma deforms this sublevel into this one, because there are no critical points in between. Okay, so I'm saying that for T large, so deformation lemma, so for T large, so by the way, this is always admissible, so GAB. The deformation lemma implies that for T large, the sup of f of this evolution, phi t chi v of h epsilon, is less, so this is for y in A, less than CAB minus epsilon. But this is impossible because this is an admissible map, okay, and the sup has to be always greater or equal than CAB. I'm sure that you are all lost, but can you follow each step at least?
Just say again why if there's no critical, why if CAB is not a critical point, then F has no critical point between the intervals CAB.
That's a Palliot-Smale condition, because otherwise you will find a sequence of critical points with energy converging to this number. And that would be a Palliot-Smale sequence. So a subsequence would converge strongly to some point, and that has to be critical for f exactly at that level. So if this is not true, so you can find the critical points with energy arbitrarily close to CAB. Oh, it's just I'm just contradicting this this fact. Yeah. So either there is a sequence of points, critical points, for which the energy converges to CAB, or there is none. So if there is none, then this is satisfied. But if there is such a sequence, then we have the Palliot-Smale condition. Okay? So typically, you have to somehow imagine this fact. So the value of the function is low at B, so I can take B to be the boundary of A, but it has to be higher in between. Okay, so one example is the so-called mountain pass theorem. So suppose that you have a chain of mountains, okay, and I consider the height function. Okay, I want to go from one side of the chain to the other side of the chain. Okay, so initial and final point are very low in altitude, but I have to cross the mountains in between. Okay, so this means that the soup of the altitude will be actually higher than the initial or final altitudes. So that's somehow a standard application. Are you convinced, or should I continue?
So, just a point. So, you had this condition about Q being not a multiple of 8 pi squared.
I'm not touching it today.
Yeah, but I have a.
Don't even think of that condition today. People are already lost with this. That will be useful somehow to get the Palais-Mail condition, but
So that's what
don't even think of, don't remind people of that condition. We're stuck with much simpler things here. No, just joking, but yeah. So okay, this looks very abstract nonsense. I told you, okay, but the proof seems to work at least. Okay. No, this, I'm sure that this reminds you of following calculus. There are many epsilons and delta. You don't understand what's going on, but if you, say, follow the proof, then it works. So, say, the proof is correct. You are just not understanding why I'm doing that, and okay. But, okay. So let me make some remarks and show you one easy example. Okay. So remark. So one, we saw that the Palais-Mail condition implies the deformation lemma. Okay. And the deformation lemma plus this weird condition star. Okay, so these two together give you, in fact, the applicability of this min-max scheme. Okay, so I just want to point out that the important things are the deformation lemma and this condition star. Okay, so suppose that you know you have the deformation lemma and this condition star, that will be enough to conclude. Okay. In fact, and yeah, somehow I go back to Sagun's comment, it is not known for QP large whether the Palais-Mail condition holds in this case. But the deformation lemma is known. Okay, so this will, I will come back to this in the next lecture if you are not all gone. Okay. The second is that, so the scheme, so this condition star produces Palais-Mail sequences. Okay, just automatically. Okay, so if you know that the Palais-Mail condition holds, then you can find the existence of critical points. But if you just know this condition star, then you apply that flow with cutoffs, and you find a Palais-Mail condition, Palais-Mail sequence at that level CAB. Okay. The third is that, well, in general, to apply this condition star, you need the functional to be low on the image of B and high on the image of A. So usually on B, you have to choose somehow good test functions which keep f low. And for A, you have to find lower bounds on f. So fourth condition, so this is kind of important, is that random choices of A and B will not guarantee this condition star. So the choice of A and B depend, in fact, on the specific problem. So let me give you an example. So example, I consider this function from RT into R defined as z squared minus x squared minus y squared. Okay, so notice that is always greater or equal than 0 on the z-axis. Okay. So let's try to draw a sort of a graph of this function. Okay. So the 0 set will be just this cone. Okay. Okay. So here the function is positive. And in fact, the scheme works if you choose A to be the unit ball in R2, S to be S1, sorry, B to be S1 in R2, and HB to be the identity on R2 times 0. Okay, so the set B will be just the unit circle in the xy plane. Okay, and I take HB to be the identity. Okay, now I consider all the continuous maps from the unit ball in R2 into R3. Okay. So I somehow cover this circle, so I complete it with some surface. Okay, you can think of it being a graph, say. Okay, so by degree theory, this graph will intersect the z-axis. Okay, so f is equal to -1 on B. Okay. But each time I intersect the z-axis, f will become non-negative. Okay? So in fact, this condition star will be satisfied. So you can choose delta to be, for example, 1/2. Okay? So star is okay. Okay, so C naught is equal to -1. Okay, and you can choose delta to be 1/2. Of course, the Paley-Smale condition is true. So you know a priori that 0 is a critical point, but yeah, suppose you don't know, then you can apply this scheme. So this is a good choice. Are you somehow convinced of this construction? well, you can verify the assumptions. Okay, so this is a good choice. Okay, what is not a good choice? Okay, so I chose A to be b-dimensional. Okay, suppose I take it, for example, lower dimensional. Okay, so try A to be just a unit ball, say 0, 1 in R, okay, and B to be just the set 0, 1. Okay, I want to replace the circle by just 2 points and the disk by a curve. Okay, so I can choose, for example, as a set B, I can choose 1 point here and 1 point here. Okay, so this will be my B. Okay, just 2 opposite points on the xy plane. And here also the value of f will be -1, here and here. But I can connect them just going around the circle. Okay, so if I do that, then the value of f along this arc of circle will be identically equal to -1. Okay, so there is no gap between the supremum on the boundary and the supremum in the interior. Okay, so this is not the right choice. The same, so you can try to choose, for example, A. So this doesn't work. Okay, try A to be now the unit ball in B3, in R3, okay, and B to be just S2. This also doesn't work. Okay, I will not spend time on it. Maybe you try yourself. But somehow the choice of A and B is somehow limited. And you can consider yourself to be lucky if one choice of A and B will work. Okay, so somehow I hope to have convinced you with this example that so somehow spheres and balls can be good choices. Okay, next week I will choose a set which is completely crazy. Okay, but it works. Okay, it will work. Okay, so I want to make a point here that the choices of A and B are usually very limited. Okay, and you cannot proceed randomly. Somehow they have to be related to the topology, relative topology of sublevels of F. Okay, so this example is in fact very instructive for the Q-curvature equation. Okay, so let me start. I'll try to do what I can in the remaining time. So I want to treat the case of lambda 1 negative and total Q-curvature less than 8 pi squared. Okay, so study of problem P when lambda 1 of PG is negative and QP is less than 8 pi squared. So this is the easy case I want to start treating today. Okay. So PG now okay, has negative eigenvalues. Which I call lambda 1 lambda k bar. Okay, and I call phi 1 phi k bar the corresponding eigenfunctions. Okay, I'm counting the eigenvalues with multiplicity. So I choose h bar as the Hilbert space of the functions u in H22 such that u bar is equal to 0. So this will be the integral of u equal to 0. And I split h bar into w minus direct sum with w plus. Okay, so this is the span of phi 1, phi k bar, negative eigenvalues. This will be the span of positive eigenvalues. I'm assuming there is no non-trivial kernel. Okay, only functions in the kernel are the constants. Okay, so there is a first lemma. So let me recall the Adams inequality. Okay, so this is the weak form. If the Penitz operator is a positive definite, then you can control the logarithm of the integral of the exponential by means of the Penitz operator. In fact, there is some kind of variant. It's a really cheap improvement of that inequality, which is the following. So let u in h bar equal to u plus plus u minus, okay, according to this decomposition, and assume this is really ridiculous, okay, so that the norm of u minus in h bar is bounded by 1. Okay, so the negative eigenvalues are really causing no trouble. Then we have still that the log of the integral of the for u minus u bar is bounded by 1 over 8 pi squared integral of u pgu plus c. So maybe I will skip the proof of this lemma, but I'm really cheating. Okay, so that lemma is telling you that when the operator is positive definite, then you have the inequality. Here, I'm assuming bounds on the negative components of u. It has to be true.
So that C depends really on the
It's depend
background
only on the background metric. Yes.
number of K bars.
Yes. This is really a cheap improvement. Okay, nothing serious. But there is a nice consequence. So this implies that, in fact, as long as the negative part, negative component of u is bounded, then we still have a negative bound, a lower bound for the functional. Because I can just use the same inequality as before, and I can prove lower bounds. Okay. So the lower bounds fail in general, but if I impose restrictions on this component of u, then I still get the lower bound. And that's important because I want to get lower bounds when I apply this kind of min-max scheme. So what is the scheme I want to apply in this case? So this is telling me what? That if I move in these negative directions, then the functional goes down, just here. And if I move in the perpendicular directions, then the functional stays positive. Okay? And if the components of the negative or in w minus are bounded, or say 0, then I get lower bounds on the functional. So we are exactly in this situation. Okay? You just have to substitute the xy plane with w minus and the z-axis with w plus. That's the idea. Okay? So proof of existence. Okay, so I take A to be a ball with the same dimension as the negative directions. So in that case, it was 2. In this case, it will be k bar. Okay, A to be the unit ball in k bar dimensions. Okay, and B just to be the boundary, so sk bar minus 1. And I consider this map HB from B into H bar. Okay, so HB, I can view sk minus 1, k bar minus 1 as embedded in Rk bar. Okay, HB of x1 sk bar to be some large constant r times sum from I equal to 1 to k bar of xi phi I, exactly the eigenfunctions of dependence operator with negative eigenvalues. Okay, so as r tends to plus infinity, so I'm evaluating now the function on large spheres in the negative eigenspaces. Okay, the quadratic part of the functional now will dominate. Okay, and will have a negative coefficient. Okay, so the sup for x in B of the functional 2 evaluated on the image over HB of x will tend to minus infinity. Okay, I'm just moving in the negative directions for r large, then the function is really going down. Okay, it's like I'm moving on big circles in this case. Of course, here the function is homogeneous, so any circle will do. Okay, here I just have to take large circles. Okay, because if I restrict myself on finite dimensional spaces, then this is really quadratic, linear, and kind of linear. Okay, so for r large, the function goes to minus infinity. On the other hand, if I impose bounds on the w minus component of u, then the functional is bounded from below. Okay, and then I can apply the previous proposition. Okay, so take H in this admissible class GAB. Okay, so by degree theory, there exists some y in A such that h of y minus is equal to 0. Okay, and this implies lower bound on the sup. Okay, so the sup, so by that improvement, so by lemma 1, so the sup for y in A of 2 of h of y will be bounded by minus c independently of h in G AB. Okay, so this implies that star, condition star, is satisfied. Okay, so on this set B, I get large negative values. In between, there will be one point for which the functional is bounded from below. Okay, so by the previous remark, okay, we have condition star, and this will produce a Pallier-Smale sequence. Okay, so maybe I will stop here for today. Next time, I will prove that in this case, Pallier-Smale sequences are bounded.
So you need that's not critical value not equal to AK pi squared for that.
I don't need it at all, no. I'm assuming QP less than 8 pi squared, and this implies the Adams inequality. This
is less than 8 pi squared.
Yeah. So I'm assuming that, and this implies the lower bound on this part. So say this implies, this lemma implies 2 of u bounded by minus c if u minus is equal to 0. And I use this to get this condition star. So this scheme produces a Pallier-Smale sequence, okay? And next time I will show that under such conditions, the Pallier-Smale sequence is bounded, so there will be a weak limit, and the weak limit will be a solution. And I will also treat a more difficult case when QP is greater than 8 pi squared. Yes?